Alright, let's look at some examples of the types of calculations we will do involving waves in pipes. First of all, let's kind of derive some equations to start with, everybody's favorite thing to do. So if we look at an open pipe, one that's open at both ends, and often we don't say open at both ends, we say open pipe or closed pipe, meaning one that's open at both ends if we say open, or closed at one end if we say closed. If it's open at both ends, we get pressure nodes at both ends and an antinode in the middle, so we can fit half of a wavelength in a pipe of length L. So if L equals half of a wavelength, then our fundamental wavelength is twice the length of the pipe. And then we have our relationship that V equals F lambda, so F equals V over lambda. And then if we plug in 2L for lambda, this is my F1 and lambda 1, then I get this expression here where F equals V over 2L. I can follow a similar process here for the second harmonic, and I'm going to get that it is 2 times the fundamental, and the third harmonic is going to be 3 times the fundamental. And so in general, my expressions are going to be any wavelength of any harmonic, it's just supposed to be an n there, is going to be 2 times the length divided by n, and then the frequency of any harmonic is going to be n times V over 2L, where n can take the value of any positive integer. So this is identical to what we saw for waves on a string, and that's because they both had nodes on both ends of the length that we were considering. Okay, so again, this would be the first, second, and third harmonic, or the fundamental first overtone, second overtone. Things change a little bit when we have closed pipe, or one that is closed at both ends, because there we have a node on one end, but we don't have a node here at the closed end. We have an antinode. So rather than having a half a wavelength here, that's an ugly loop, we get just a quarter of a wavelength. So if we fit a quarter of a wavelength in a pipe of length L, that means our fundamental wavelength is actually 4 times the length of the pipe. So you can get a lot lower frequencies out of closed pipes than you can out of open pipes. And we can use the same process where F equals V over lambda, and that gives us V over 4L. Follow similar things here, where in this case we can fit 3/4 of a wavelength, because each of these segments is a quarter, and we can fit 3 of them in a length L, and you end up lambda, that wavelength would then equal 4/3 L, and plug into F equals V over lambda, and you'll get this expression here, and you'll get that it's 3 times the fundamental. Do the same thing here. Here we have 5/4 wavelengths that fit in there, so the length is 5/4 times the wavelength, and you end up with this guy, 5 times the fundamental. So our equations are a little bit different. The wavelength for any harmonic is going to be 4L over n instead of 2L over n. The frequency of any harmonic is going to be NV over 4L instead of 2L, and our n values are going to be, they're going to be every other positive integer. So just the odds now. Okay? Now, the naming scheme gets even more complicated. Here we would just still call it the first, third, and fifth harmonic, corresponding to the number of n that we're plugging in. But we would call this the fundamental, and we would still call this the first overtone and the second overtone. So it's basically just the first sound that you can hear above the fundamental is the way they use that overtone. Alright, here is a nice little summary of everything we talked about. So here's the equations for open and closed pipes. By saying resonant waves, I mean these are the waves that fit with either a node or antinode at each end, and they are the ones that will persist over time, because the other ones will all cancel out with their reflections, because they won't be what we call in phase with each other. Another thing we need to look at is these equations include velocities, and we're talking about the velocity of the wave. And if this is a pressure wave through a gas, that's what we consider a sound wave. And that varies slightly with the gas. It also varies with temperature. So if it doesn't specify, we are going to assume that it is air at 20 degrees Celsius. So go ahead and plug in 343 for all your velocities, unless it says otherwise. If it's colder, that actually slows down the sound wave a bit. If it's hotter, it speeds up. And if we fill a pipe with helium, then we have a different speed of 1,005 meters per second. Okay, now on to some examples. Let's say we've got a 25 centimeter pipe, open at both ends, and you blow over one end. We want to figure out the frequency that we will hear. Now the frequency you hear is the fundamental, because that's always the most dominant sound that you get out of any musical instrument. So we want the fundamental of an open-ended pipe, so that equation is just V over 2L. And it didn't tell us otherwise, so we're going to assume that this is nice room temperature air. 2 times the length of the pipe. Be sure and convert that to meters, because this was meters per second, so we need this to be in meters so that the meters cancel out. So we just end up with 343 divided by 2 times a quarter, and that works out to be 686 hertz is the fundamental, and that's what we're going to hear. The other harmonics that are possible, if it's open, we get all the harmonics. So we'll get the second harmonic, which is going to be at 1372. We will get the third harmonic, which is going to be at 2058. And in general, we will get 686 times any number n. Erase my comma there. So n can be any positive integer. Okay, now what if we take that same pipe and we cover one end, so we could tape over it or something like that, and we blow over the open end? Well, now it's a closed pipe. We're still going to hear the fundamental, but the fundamental is going to be different because we'll only fit a quarter wavelength in there. So we're going to plug into this V over 4L. So 343 times 4, our length is still 25. So 4 times a quarter, that's just going to be 1. So this makes it nice and easy. And our fundamental frequency goes down to half of what it was before. So we get, erased everything. Sorry. We get 343 hertz is the fundamental. Now, the other harmonics that are possible, we won't get the second harmonic. We will still get the third. So we take the fundamental times 3. That's going to be 1029. We don't get the fourth, but we do get the fifth. Fundamental times 5 is 1715. And in general, we're going to have 343 times n, where n has to be an odd integer. Okay? Now if we decide we want to have a little fun and we're going to fill our pipe with helium, it is still covered on one end, and we want to know the fundamental frequency with helium. So if it is a closed pipe, we're still using V over 4L. The only thing that changes is the velocity of the sound. It's no longer 343. If you remember on this other diagram here, it's 1005. Get my pen back. So 1005, and we divide by 4 times a quarter again, so this just gives us 1005 hertz, significantly higher than the 343 we had when we had just air in the pipe. Alright, one last example. This one's a little trickier. If we say we've got an organ pipe, and 3 of the overtones are 660, 1100, and 1540, and we want to figure out if the pipe is open or closed and what the fundamental frequency is. Alright, so if I look at the difference between these two frequencies, it's 440 hertz. If I look at the difference between these two guys, it is also 440 hertz. So now I got to figure out, well, is this an open or a closed pipe? What do I know about those things? If it's open, then I know that the separation between between each overtone is equal to the fundamental. So if it's open, then my fundamental frequency is 440 hertz. If it's a closed pipe, then I'm only getting every other harmonic. So if this is, say, F3 and that's F5, there's a difference of 2 times the fundamental. So if 440 is twice the fundamental, if it's a closed pipe, then the fundamental would have to be 220 hertz. So how do I know which one is which? Well, I also, in addition to knowing this information, I know that the any harmonic has to be a multiple of the fundamental. Well, is 660 a multiple of 440? No, it's not, because 440 times 1 is 440, 440 times 2 is 880, so this cannot be the fundamental frequency if I'm getting an overtone of 660. This guy is not a fundamental, or is not a multiple of 440, neither is that guy. So none of them are multiples of 440. But are they multiples of 220? Yes, yes, and yes. So there we have it, folks. If you look at the separation, you can figure out what the 2 possible fundamentals would be if it were open. It's just equal to the separation. If it's closed, half the separation is your fundamental, and then you can see if these harmonics are multiples of this guy or that guy. And you are going to see a problem like this in the future, so you might want to take some notes, take a minute to digest this one. Okay, see you next time.